DeBroglie suggested that if light, all types of EMR, could have particle properties, then particles, such as electrons and protons, could have wave properties. So he suggested that the wavelength of an object is related to their momentum. So we are going to take the momentum of object. So if a particle has momentum like a proton, then it must have a wave property according to DeBroglie. So we'll look at the momentum of a wave. So momentum of an object is P is equal to M times B. And momentum of a wave is P is equal to H over lambda. So if both of these are equal to P, and we can say that this object has wave properties, we're going to equal these formulas to each other. Mind blow, right? Now, note, this formula is not on your data sheet. It is not on your data sheet. It's a formula that you need to derive. Now, if you're asked something like which principle are you using when you use this, you're still using the principle of wave-particle duality. Okay? So this still supports wave-particle duality principle number 9. It's just applying it to objects. Before we are just applying it to EMR, now we apply it to objects. So it's still like you use this idea and assumption and you make this formula using that principle. Now, again, note that H is in this formula, but there is no E, no energy to cross off EV, so you must use the Planck's constant of 6.63 times 10 to the negative 34 joules times seconds, okay? Because the rest of the variables only work with joules, not with EV. So think the only time you get to use it with EV is when you can cross off EV somewhere, okay? So the wavelength of a particle, this formula is often referred to as the DeBroglie wavelength, okay? So if we rearranged it and solved for wavelength, H over mv. So this is referred to as the DeBroglie wavelength. So if a question asked you, find the DeBroglie wavelength, then that's what that means, okay? Oh. So, an interesting application of this is electron microscopes, because electrons are used for microscopy. The idea of matter waves is not simply abstract physics that has no practical application. The wave nature of electrons has been used to build microscopes capable of amazing magnification. Their reason for their amazing magnification lies in the very, very, very small wavelength that the electron has. The usable magnification of a microscope depends inversely on the wavelength used to form the image, blah, blah, blah. And then there's a really cool picture of an insect. Okay. Have I showed you my pictures I've taken with electron microscopy? I can show you. I'll show you after. It's only well, I won't tell you what it's of. I'll make you guess. So, the wavelength, the particle, blah, blah, blah. But how do you demonstrate that particles have wave properties and give support to this? Well, we already talked about that. I showed you examples from that book. But as I said, J.P. Thomson, son of J.J. Thomson, demonstrated that electrons could be diffracted, similar to the Young's experiment. So when a beam of electrons went through, it diffracted and made an interference or diffraction pattern. That's a wave, definitely a wave-like observation. Okay? So, but I think we've talked about that enough. Okay? You get that? Something that we expected to not make, wave-like pattern did. Okay, so how do we put this into practice with the formulas and things like that? So our first example, let's do